So this talk is on RDDs, DataFrames, and Datasets in Apache Spark. It's not going to be as code heavy as Runar's. I don't think I used the word monad once, but hopefully it'll be enjoyable. Anyway, the general idea here is that RDDs are what most people are used to using up until recently, when everybody was saying, no, 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 you want to use DataFrames. And then now people are saying, well, you know, maybe there's this new thing called datasets that we'd like you to migrate to instead. And what we're going to do is compare and contrast the three of them a little bit to give you an idea of what datasets are going to start looking like moving forward. So the end game here is a little bit of background on RDDs, a little bit of background on DataFrames. For those of you with Spark knowledge, that's going to be a little boring, right? But for those of you without Spark knowledge, you'll get an idea what the APIs look like. And then we're finally going to see datasets, and that's sort of the way forward. So that's sort of the intent behind this. I will tell you up front, I am not a Spark committer. I do a lot of Spark training, but I'm not a Spark committer. So if you ask me under the covers, how is that implemented, I'm very likely just to say UTSL, because that's exactly what I'm going to have to do if I try to figure out, you know, is this using this particular capability under the covers? All the code is out there. There's a significant amount of it. For those who are not familiar with Spark, the Spark code base is largely written in Scala. So it's and all of the Spark committers, particularly the guy behind Datasets, is actually absolutely a fan of Scala. When I told him I run the Philly Scala meetup, he looked like he was about to start applauding. So, you know, I think he's had to fight to get people to use Scala, so he's very happy about that. All right, so the three things that we're going to be discussing here are RDDs, which is just short for Resilient Distributed Dataset, DataFrames, and Datasets, which kind of has an unfortunate name, I think, but we'll get to that. So what's an RDD? Basically, an RDD is the building block of Spark. It's what you see under the covers. It was the original API that Spark exposed, and pretty much all the higher level APIs decomposed down to RDDs under the covers, whether they expose them to you or not. There's still plenty of people out there who code to the RDD API. They have a couple of characteristics. They are compile time type safe. They're lazy. Okay, so in that sense, they kind of work like streams. So when you do things like map and filter over an RDD, you get back another RDD, but you're not actually processing data yet, right? The data doesn't get processed until you call something that says, hey, I want something out of you, at which point the whole thing gets triggered. So they're lazy in that sense. They're kind of based on the Scala Collections API. If you look at them, if you're familiar with the Scala Collections API, you'll look at them and say, oh, I recognize half these functions because they make sense. They were deliberately built around the model of the Scala Collections API, to the point where it can actually be somewhat confusing. If you look in the RDD API, this is still the case. There are two collect functions. In classes we've done, sometimes people get confused by this. The first collect function looks exactly like the collect function in the Scala Collect API, the one that we commonly use to sort of combine map and filter, right? The second one is the RDD collect action, which drags data back into your application from the nodes. And so people look at this and they say, why are there two collects? I don't understand. And the reason is it's based on the Collections API. So here's an example of some code. It's kind of made up, but not that much made up. That file, the demo I'm going to be giving, actually, we'll be looking at a file very similar to this. The idea is that there's a text file out there. We're going to read it in. Then we're going to parse it. Okay, so it's got some tokens in it. So we're going to use flat maps so that I can discard. Note that I'm not complaining, but I'm going to discard the ones that don't have 4 fields in them. Right, so I only want to process the ones that have 4 fields in them. And then at the bottom, I'm going to extract a key and a value. Right, filter out those where the key doesn't match EN. That in this particular case is the code for the English Wikipedia. And again, the demo, I'm going to talk about this in more detail. We're going to do a reduce by key. In other words, I'm going to combine and add up all of the values. Then I'm going to take the top 100 of them and loop over them and print them. Okay, pretty straightforward if you look at it, but you kind of have to look a little bit to figure out what's going on. What are we trying to accomplish here? What we're trying to accomplish is to count up the number of hits on the project, right, in a distributed fashion. Okay, so one of the problems with the RDD library that people complain about is this is a little bit opaque. It's a little bit difficult to see what you're trying to accomplish because you're looking primarily at the how. Right? They're type safe, which is the positive thing. They're compile time type safe. RDDs have types. They can be an RDD of an array of string. They can be an RDD of a case class. They're compile time type safe. This is a real win. But the downside is, as I said, they express the how more than the what, which means it can be hard to look at something and say, all of this gibberish is computing an average, right? It's a little difficult to read it and understand what's going on. They cannot be optimized by Spark. They are entirely lambda-driven. Spark can't look inside the lambdas. They're opaque. So it can't do any optimization on your behalf. I'll show you an example of what I mean by that. They are slow on non-JVM languages. Now in here, we probably don't care, right? But an awful lot of people are using Spark with Python, for instance. And we're talking significant slowdowns if you try to use RDDs from Python for reasons I'm not going to bore you guys with in here, since we don't care. We get to use the JVM. Right? So it's too easy to build an inefficient set of transformations. So here's an example of an inefficient transformation. Right? We're doing the reduce before we do the filter. So we're reducing the whole data set, counting the whole data set, and then filtering some parts of it out. Okay, that is not the right way to build this. That is very inefficient. You want to do the filter first, so you're doing less work. As it turns out, for reasons having to do with the way Spark works, filter is more efficient than reduce by key anyway. There's no network traffic involved in a filter. There is network traffic involved in a key-based reduction like that. So you want to do the filter before you do something more expensive like a reduce. Here somebody has coded this. I have coded this intentionally badly, right? But Spark can't help you here. It does exactly and only what you tell it. So that's a problem, because it's very easy to write something that doesn't perform very well. So this is what led to the DataFrames API. The DataFrames API was intended to provide a higher level API, something that is a little bit closer to expressing what you're trying to accomplish rather than how you're trying to do it, in a way that can also be optimized better by Spark. Right? So it gives you a query language. If you look at the DataFrames API, it's really a DSL in both Python and in Scala. It's a DSL. And it builds a query plan under the covers. Interestingly enough, that same query plan can be built with a SQL statement. They work hand in hand. So that you can say, I'd like to build my query using this DSL, this type-safe DSL, type-safe-ish. I'd like to build it with SQL, and the net result is the same thing. All right, I'll show you what I mean by that in a minute. So this is the exact same piece of code, or exact same work that we're trying to accomplish in the DataFrame API. So again, what we're doing is we're loading up our RDD and converting it into a data frame. Okay, we're giving the data frame column names. The characteristic of data frames in Spark is that they have schemas, and a schema in Spark basically means it is something that we can view as a column, and columns have names and types. And that's basically it. Whether it's really a columnar store is kind of irrelevant. You can, for instance, read a data frame from a JSON file. Well, that's certainly not a columnar store. But if you can pretend that it has columns with names and types, then it can be represented in a data frame one way or another. So that's what we're doing here. We're converting our RDD into what conceptually looks like a table with a project column and a num requests column. Then we're doing a group by, a sum, an aggregation of a sum, a limit on that, and then we're pulling. Show basically pulls 100 of the elements back, so show is the action. Show kicks off the execution, pulls 100 records back, and displays it in a table that looks like it was ripped right out of the MySQL REPL. Okay, I can show you an example of that as well. And again, you can do the same thing in SQL. This does the exact same thing. And I will contend that this is easier to read than the RDD version. Right? I mean, you look at this, if you have any idea what SQL does, this makes sense. This is not that much harder to read. So the argument behind one argument behind using data frames is that you're closer to what you're trying to do rather than how you're trying to do it. Kind of the same way as if you're talking to an RDBMS engine, unless you're a DBA with loads of query hinting, foo, what you typically do is you give the SQL statement and you're not worried about how the RDBMS goes in and figures out whether to do a table scan or which indexes to use. All you want is the result, and you express what you want, and you let the RDBMS engine on the covers figure out the most efficient way to do that, right? And that's the general idea behind the DataFrames API. Let Spark figure out how to do it for you. It turns out they are, in fact, optimized. I stole this diagram from Databricks. But the general idea here is that whether you start out with a SQL AST, a parsed AST, or a data frame, what ends up happening is that you're building an unresolved query under the covers. Right? So at the end of the day, when you're ready to execute an action, you've built up this query plan. Well, these guys have enough of a database background that they optimize their query plans the way an RDBMS does. What will happen is that they use this catalog down here, which basically is just a list of the available user-defined functions. Okay, so I put that in there so we can ignore that now. Everybody asks what the catalog is. It takes that unresolved logical plan and it figures out the actual logical plan that it wants to use. I'm going to show you a diagram about what I mean by that. But it does some optimizations to produce a logical plan and then some further optimizations to produce an optimized logical plan, at which point it starts to construct physical plans. How do I want to execute this? How do I want to express this abstract notion in terms of the RDDs that everything ends up being built on under the covers? Okay, so having done that, then it can run it through a cost model and choose the most efficient physical plan, which then dictates how to build out the RDD chain to implement this query. Right, so what we get out of using DataFrames is this sort of optimization that goes on under the covers. And in classes that we give, I always sort of describe it like this. You know, I'm obviously old enough to have plenty of gray hair, and I remember doing C back in the 80s when they told you things like, well, you know, if it's not fast enough, you can use a pound ASM keyword and throw some assembler in there, which nobody really liked to do, but you could, right? But then there came this inflection point where the optimizers of the compilers got so good that nobody thought that that was a good idea anymore. Right? Why do I want to waste my time making my code unportable writing assembler when the optimizer is so good that I'd have to work really hard at it? And to me, that's sort of what the Catalyst optimizer is. It's going to keep getting better. And so therefore, if I don't have to spend time tuning my RDDs, I can focus on the business problem. Right? So that's the general idea. So here are some of the, this is an example optimization. We use this one a lot. So we're doing a join here. But there's something wrong with this join. Anybody see what's wrong with this join? Well, it's not what you're joining. It's the fact that you're doing the join before you're doing the filter. If you look carefully at the filter is against the event. I want to do the filtering first because that reduces the size of the join. And a join in a distributed computing environment like Spark can mean network traffic. Right? So the less data that I have to join, the more efficient my join is going to be. So if this were RDDs, that would be bad. Right? That would be inefficient. So what happens under the covers is that there's the logical plan. In other words, this is essentially your query plan. This is what you typed. I could execute this under the covers if I wanted, but instead Spark uses some heuristics and says, hey, you know what? That's inefficient. That join is not efficient. The filter should come first. It automatically reorders things and pushes the filter down below the join. We read these bottom up, okay? So the data that we're reading is at the bottom in this diagram. Right, so it decides that this needs to be moved down automatically. Another thing that it will do that I'm not showing here is if you put multiple filters in a row, based on certain heuristics, it can coalesce them into one filter operation. And then it may also do something like this. Okay, it might notice that the events data source is intelligent. In other words, in this particular case, maybe it's a Postgres table. At which point, I can shove the filter all the way down into the database. It just becomes a where clause. Right? So I never even manifest the data in memory. The database takes care of doing the filtering for me. Other examples of that kind of intelligent filtering are Parquet files. Right? A Parquet file is a very efficient column-based storage. Makes columnar access extremely, extremely efficient. So what Spark will do with a Parquet file is if you have a Parquet file that has, say, 300 columns, but it determines that at the end of the day, you're only using 3 of those columns, it will effectively push the select down into the Parquet and say, I don't need to manifest all 300 columns just to throw away 297 of them. I'm only going to pull those 3 columns out of the data source. So it has some built-in intelligence that it can make decisions like this. And my contention is that this is not the kind of work you really want to be doing yourself. Right? So if you work at the RDD level, this is kind of a pain. It's a pain to get right. It's a lot of work. Why not let the optimizer do this for you? And then you stay closer to the problem you're trying to solve, and you don't have to worry about the implementation detail. The bits become sort of irrelevant. They are faster. Another diagram I stole from Databricks. So you'll note that Python, as I said, is much, much slower. than Scala. The reason is that the lambdas are really written in Python in RDDs, and they're CPython. It's not Jython because you can't use Python packages like NumPy and scikit-learn if you do that. So that Spark actually has to shove that stuff over to a running Python VM, which does the work and then shoves it back. So every lambda that you use in RDD land in Python does that. Okay, and it's really slow, but you'll note that DataFrames are even faster in general, Scala to Scala from RDDs, and that's the optimization going on in general. It's able to make more intelligent decisions and speed things up, as well as level out the performance across languages. This is part of the pitch, right? This is the pitch to use DataFrames. But here's the problem. We've lost type safety, okay? So this is really horrible for a lot of people. You'll note that the type, if I do a collect on the DataFrame, which says to Spark, hey, I've done all the work I want to do on this thing, run the job and pull the data back that's left. I want to look at it in my application. Note that the type comes back as an array of something called row. And rows are not type discriminated. Each column has its own type, but that's not exposed to you as part of the API. So to you, it's an any. I mean, you can't see it as anything else other than an any. So you've lost compile time type safety. You have asserted that, look, my project column is a string, my page title column is a string, my num request column is a long, but you don't see any of that in the code. All right, and you can see an example of that further down here. When you do the collect, if you need to map this back to real types to play with it, now you're doing stuff like as instance of, which none of us likes to see, right? That's pretty horrible. And extremely error prone. Like, what if you get it wrong, right? Well, you've run this long job that takes 30 minutes to chew through a terabyte of data, and then hits the collect and blows up with a class cast exception, right? So who wants that? So this is part of the reason that they've moved more toward this thing called datasets. Now that they have the infrastructure in place to do the optimizations, isn't there a way maybe that we could drop something in place that gets back some of the type safety without losing all of those optimizations? Because even now, even before datasets, what you can do is do a lot of work in DataFrames and then drop down to RDDs to do the rest of your work. You can always convert a DataFrame back down to an RDD to go back to type safety, but you immediately lose the optimization that's done by the Catalyst optimizer. You're back on your own, right? So isn't there some sort of middle ground? And that's sort of where the impetus, my understanding of the impetus of datasets came from, right? Because we want to get back our compile time type safety, but we'd also like not to lose all the optimizations that this optimizer, this Catalyst optimizer, can provide us under the covers. So this is what datasets are attempting to at least start providing. So what are they? First of all, they're an extension to the DataFrames API, which means that they operate on data through the SQL context. Okay, when you create one of these things, you create it through the SQL context the same way you create a data frame. All right? The second thing that they do is that they are conceptually similar to RDDs at some level. In other words, you get back your lambdas and types, okay, with data sets. You are now operating on domain objects that are Scala, or if you prefer Java, types that are manifest in the compiler, and you get some compile time protection back. Now, there's this thing that they've been introducing into Spark called Tungsten. One of the things that they're trying to do is make memory management in Spark much more efficient. So instead of storing stuff, for instance, on the JVM heap, which immediately runs into all kinds of garbage collection problems, they're starting to move memory management of Spark data off heap into this unsafe area, and they're doing it with this thing called Tungsten. Tungsten provides not only off-heap memory, but it has this compact columnar-based storage that allows them to operate directly on this stuff very efficiently in memory. So Tungsten's fast in-memory encoding is used in datasets. So instead of RDDs, where everything is stored as Java objects, this thing actually uses Tungsten. Now, how does it do that? It has to know something about your data in order to do that. And it turns out that what it does is it uses these encoders. We'll get to that in a second. Okay, but it basically uses this special kind of code generation to take your domain objects, your case classes or whatever, and generate code on the fly, literally under the covers, bytecode, that can access these things and map them from domain objects into this Tungsten store and back again by analyzing what it is that you're actually working with and generating code on the fly for this. right? And it also provides easy interoperability with the DataFrame API, which is not something RDDs provide. So what do all these bullets really mean? These bullets really mean that you get back some of what you had with RDDs, but you're operating in the DataFrame world. Okay, you're not dropping entirely back down into pure RDD level. This stuff all boils down to RDDs under the covers, but that's all being managed for you. You're operating at a higher level. You're still able to think of things in terms of your data frames, your columns, and their types, but you can switch back into something that has stronger compile time types. Now, this is an experimental API at the moment. It showed up in Spark 1.6. It's becoming their development focus for the next several Spark versions. They're starting to do things like take Spark streaming and move it toward a dataset or DataFrame model as well. Spark streaming currently is their streaming model, and it produces RDDs over time. So it takes a stream of continuous data and chunks it up into RDDs as it comes in. They're moving that up a level to give it access to DataFrames and datasets as well. So this is becoming the forward focus for Spark. Okay, so like an RDD, a dataset will have a type. So this is an example of creating a dataset from a JSON file. Presumably, this JSON file has at least two fields, name and age, one of which is a string, one of which is a long. Okay, Spark can actually do some analysis of that file and determine, do some sampling and figure out what the common fields are in the records, and then generate a schema on the fly. That's called schema inference, and it happens at the DataFrame level already. You can do that. But in this case, what I've done is I've said, read this JSON file into a data frame, and then I'd like to view that data frame as a person object. And when I do that, when I call that .as, I get back a data set. So it's basically mapped the data frame columns, in this case, name and age, into my case class. So one obvious question is, how does it do that? It does that by name. All right, so the names kind of have to match. At this point, I have a data set that is based off of a data frame, and I can start doing some fun stuff with it. And they've also changed the notion of a data frame. A data frame is now just a data set of type row. In other words, it's a data set, but it has a type that's not all that useful. Right? So they've basically taken the whole idea and extended it all the way across the board. Everything is now a data set. This is an example of RDDs versus data sets. You'll note that they look very, very similar. The first lines are slightly different. In the first case with the RDD, we use the Spark context to read a text file. In the second case, we use the SQL context to read a text file, which will bring us back a data frame, and then we convert that data frame to a data set. So we're saying this is a SQL file of type string, because I haven't broken it apart yet. Right? The second line looks exactly the same, except that one is RDDs and one is datasets. And so the second line is actually going to use the more efficient encoding. It's actually going to generate an encoder for our particular type to be able to map this to and from that internal, highly efficient tungsten-based column store, whereas the RDD one won't. It's going to be dealing purely with JVM objects. And the final lines are almost the same, but the second line is somewhat shorter, and I've called those out specifically here. So you can see that they're both doing a group by that looks identical, but in the RDD case, in order for me to count them up, I have to do that via my own map. Whereas in the second case, in the dataset case, I can use a count aggregator that looks an awful lot like the SQL count star aggregator or the count aggregator in the similar DataFrames API. Yes? I'm sorry? You'll get an error. You'll get a runtime error. Yeah, you'll get a runtime error. In fact, I would encourage you, I'm going to give you the demo that I'm going to do. I'm doing a notebook demo, but the source will be available. I would encourage you to pull the source for that and do exactly that in like the Spark shell and see what happens.
But that will give you the same problem that you still have the runtime blow up.
It's not perfect, right? But I mean, think about it this way. What you're saying is you're still going to, the question was, this gives you the same problem. You still get a runtime error instead of a compiler time error. But you're always going to run into a little bit of that when you're reading an external file, right? Because you can't compile that external data file, right? So it's giving you, it's not perfect, but it's giving you more than you get with an RDD. Even with the data frame, what it's going to do is infer the column name from it will make the column names up, right? So yes, you're absolutely right, you have a problem here, but with data frames, let's contrast this. So in this case, what you have is, if you read the file in and it doesn't have a name field, it in fact has a first name field, right? You're gonna get a runtime error. So contrast that with data frames. You read the data frame in, you get a first name column in the data frame, but what if your code then says, I want the name column? It's the same problem, right? You're still gonna get a runtime error. So the problem is just moved into a different place. So it's not really dramatically different. Okay, back here, the only other point I wanted to make here is that the data set code is more visually compact. I think it's a little easier to read. It's closer to the what I'm trying to do rather than the how I'm trying to accomplish it, right? I might be heretical and not even comment this, although I probably would anyway. But whereas if I don't comment the RDD code, it's very unlikely that my own self 3 months later will understand at a glance what it is I was trying to accomplish, right? It will also likely execute faster than its RDD counterpart. Okay, because of the encoders and because of the tungsten format. Here are some of the advantages that data sets are providing. And again, this is ongoing work. So they tend to use less memory. Because Spark builds these encoders, does this on-the-fly code gen, it has a greater understanding of your domain objects than it would within the RDD world, where they're just more or less opaque and on the heap, right? So because it understands that, it can figure out how to store them more efficiently. So back again, it generates these encoders to translate your in-memory objects back and forth to this compact in-memory encoding. And it can actually work right out of the encoding. It doesn't have to serialize to that format and then deserialize it back out into a Java object to operate on it. It can actually say, okay, you want these things of type person, but I'm going to store them in this other format, this other compact format. Whenever you need them back as a type person, I've got this efficient encoder that I generated to pull this stuff out, but I'm going to leave them in that compact format, and I'm going to generate these encoders so that I can actually pull the data right out of that compact format and operating on it directly in that format over the chain of operations. I'm going to minimize the amount of work I need to do in the JVM here. And I'm going to maximize the amount of data I operate directly in this compact off-heap stored format. All right, so this way memory is conserved because the format, the tungsten format, is more compact than the on-heap format. It turns out it's even more compact than if you serialized it and stored it on heap. And the speed is improved by the custom code generation, right? You're not paying the penalty of serializing and deserializing. You're operating right out of this compact format. So this is an example of the space efficiency, at least in some cases that they're observing. So if you implement one thing in RDDs and then turn around to implement it in data sets, you can see that for this particular data set that they did, it's a significant difference. Okay, I believe that's data size in gigabytes. Same exact kind of job, less than about a quarter of the size consumed in memory. So this is really useful for those of us who struggle with running out of memory when we're running these big jobs, right? Again, serialization, if you think about it, Spark has to serialize data, and it has to do it a lot, right? It has to send data across the network whenever you get to a situation where, hey, I'm grouping things by this key, right? Well, that key may be, the values for that key might be distributed across your cluster. So by definition, you're looking at shuffling data across the network to get that stuff aggregated in one place. And in order to do that, that data has to be serialized, right? There are other cases where Spark has to dump data out to disk. It turns out it dumps it out to disk when it does those network shuffles. It also dumps it out, or can dump it out to disk in certain forms of persistence, caching. Anytime you have to do this, it has to serialize it, and you're going to pay that serialization and deserialization penalty. So the faster that you can make this, the better off you are. Right? So what typically is done in Spark 1.5 and before is they tell people, look, you can use the standard Java serialization library for this, but we recommend in your production jobs that you use this thing called cryo, right? Because cryo is much faster and much more compact, right? So this is faster even than that, right? The serialized data in this tungsten format is often 2 times smaller, which reduces both your network and disk use. right? This is really good if you're moving a lot of data across the network. Another stolen diagram, but this gives you an example of speed of serialization and deserialization. So it's relatively slow with Java. You can see why in 1.5 and prior they're saying use cryo, because it's significantly faster. But you go to the datasets encoders, and I mean, we're talking huge difference in speed for serialization and deserialization. So again, this is the pitch for datasets, right? You definitely want to be using this as much as you can moving forward, because you're going to get this benefit as well. But there are some limitations. Okay, one limitation is they're experimental. They are marked experimental. If you look in the API docs, it says experimental. Everybody asks, what's experimental mean? What experimental means is, look, we think this API is right, but we may decide that we're wrong and we may change it. This happened with the DataFrames API between, I think, 1.3 and 1.4. They changed everything. They changed a few things, right? So your code breaks, or at least you have deprecation warnings. So you have to be aware of that going in, that this is still experimental. It's also not done. The APIs are complete, as I found out when I was hacking my demo up again last night. There are some things that are missing that are available elsewhere. For instance, with a data frame, you can do an order by to sort the data. With an RDD, you can do a sort by to sort the data. Those are missing in the Dataset API right now, as are some of the aggregators. So there are these general purpose aggregation functions and general purpose aggregation capabilities that you can build on, but the common ones that you would hope would be there, like .sum, they're still missing. So this is still a work in progress, and that's why they're calling this a preview. So you kind of have to use it with a little bit of understanding that you may have to change your jobs down the road when Spark 2 comes along. And then I find this term really hard to Google. Okay, within the training team, we have been kind of complaining that datasets is too confusing. You can't Google it, and what do they mean? Do they mean data we're reading? How's this different from a resilient distributed data set? But this is the name. So I just Google for Apache Spark datasets and resign myself to all the extra typing. So I do have a code example. I'm going to have to try to mirror the display to do that. I will point out that, that I do have a more resources piece of this slide, and the source to this slide deck will be out there. So I'll tweet where you can look at this slide deck in live form sometime later today, and then those who want access to the kind of crufty revealed JS source will have access to that as well. But in the meantime, I'm going to mirror my display really quickly here. All right, so where I'm going to go next is to a Databricks notebook environment. This is one of the perks of doing some training through them, as I have access to this thing. There are a number of notebook environments out there. Some of you probably use the Scala notebook. There are Spark-based notebooks as well. Jupyter and Zeppelin are probably two of the most popular Spark-based ones. The Databricks people, that's their product. So in addition to paying people to maintain Spark, they have this notebook product. And the resolution is really small here. Okay, make sure everybody can read this. Okay, is that readable to everybody? All right, so this first line, I'm attached to a cluster that I spun up a while ago. This first line is basically to make sure that my file is out there. Databricks has this, usually when you do Spark, you're reading from some sort of a distributed store like S3 or HDFS. What they've written is their own sort of local file system they call DBFS. And it really is supposed to look like HDFS, but it's really backed by S3. And they have these special escapes that allow me to do things like this to see, is my file in fact still out there? And let's hope that I've got till 10, right? All right, so we can see that the file is actually out there. What this file is a file full of edits from Wikipedia. I pulled it down last night. You can see in the file timestamp that it's from 2200 last night. I believe that's UTC, right about the time that that the debate was going on. So we should see some interesting stuff at Wikipedia during that time. So the first step is, how big is this? All right, so it's about 91 megabytes, right? It's not huge. This is not what I would call big data, but if we did big data, we'd be standing here forever. Okay, so we're going to create an RDD. Now, the interesting thing about this is that because it's reading a gzipped file, there's only going to be one partition because you can't really split up a gzip file and unpack it. It's not built that way. You can't say you take half the gzip file, you take the other half, unpack those two pieces, and we'll put them back together. So we only get one partition out of this, which means that we don't have very much parallelism. So I'm going to beef up the parallelism a little bit. And then I'm going to see, let's make sure, see how many records are in there. Now at this level, we're at the RDD level, right? I'm doing pure RDD, old style Spark. Hopefully this thing will return. We're getting there. Okay, so about 7.5 million rows of edit data in there. So what do they look like? They're basically files full of 4 fields, right? And the first field indicates the Wikimedia product that's being, where the edit has occurred. So this is consolidated across not just Wikipedia, but all Wikipedias, all languages, as well as things like Wiktionary and Wikiquote and all of the Wikimedia products. So the first field will distinguish what it is that we're looking at. The second field is the page that's being edited. The third field is the number of, I'm sorry, not edited. This is accesses. The third field is the number of accesses during this hour. And the fourth field is how many bytes were actually sent over the network. Okay, and this is actually the list of what these things mean. So these are the descriptors. If you want to go back, I've got an HTML and a source runnable version of this that are going to be available in the GitHub repository. So you can actually read this as HTML and then pull the source into the Spark shell if you have the data file. So that we're not, one of the things that Spark does, if you run a Spark job, and you read the file top to bottom, and you go all the way down to the bottom, and you say, okay, pull back the data I want, and it's finished, and it's pulled all this data back to your application. The nodes, the executors they call them, the processes out running on your behalf on the cluster, all promptly forget about all the data. Okay, so if then you do another action against this RDD, you want to pull back the count, it has to reopen the file. In this case, unzip it, reload it all, process it, fire all the lambdas again to pull that second thing back. This is why we have caching. Caching, there are a number of forms of caching, but the default is to try to cram the whole thing into memory. And so that's what we're going to do here. But caching is lazy. So when I say cache on an RDD, it basically says, okay, whenever you run that next action, I'll save as much of the data as I can. Hence my need to run the count. Now at this point, I'm going to make use of something here to pull up the UI. This is just the standard Spark UI. But Databricks notebooks make it easy for us to get there. So you can see that cached in memory now, we have this thing called page counts RDD2. This is what I just cached. And it's storing about 1 gigabyte of data on the heap across the entire cluster. Right? So across the cluster, when you add up all the data being cached, it adds up to about 1 gig. Save that thought because that's going to be more important as we get further down. So this is a variation of slide 5. Where what I'm trying to do in this case is calculate requests per page. So there's my flat map, right? This is my way of both parsing the data and tossing out the bad records. You know, if it's good data, return a sum. If it's bad data, return a none. And then flat map to unpack it, right? And then I'm going to filter it. I only want to be looking at English Wikipedia, so I only want the EN project. And then once I've got that, I don't need the project anymore, so I want to map it down to a 2-tuple. Which is a special kind of RDD, as it turns out, a pair RDD, which allows me to do key value operations, at which point I'm going to do a reduce by key to sum up all of the num requests per page. Then I want to do a sort by. I want them in ascending order because I want the top 100 of them. The take is the action. That's going to fire the action, pull this stuff back. And then this final for each is actually just running on a Scala collection. And this will take probably on the order of 30 seconds or so. And I think I'm running out of time. Oh, I'm sorry, 9 seconds. So there you can see this is the list of stuff going on, but I've got some weird stuff in here like special search and special blank. Turns out there are a whole bunch of special pages, pages where people can talk about pages, pages where people can have back channel conversations, user pages, and I don't want those. So I'm going to run another version of this that removes that stuff. This should take another 9 seconds or so. All right, and now we can see the topics. This one cracks me up in particular. Okay, so apparently this is what happens when Mitt Romney comes out and says Donald Trump is a jerk. Everybody wants to know about Mitt Romney's dog on the roof, in the carrier on the roof of his car, all over again, right? So you can, this is, I don't know, this is an interesting data set just because I get a laugh out of it. All right, so there, again, this is just emphasizing that I could get this wrong and Spark wouldn't be able to help. So I'm not going to bother going through this. This is just a parsing class. Here's how I do the same thing with DataFrames. Okay, so notice I have 3 filters here. If I were to show you the query plan, you would notice that they're consolidated. And you can do that easily. I can take one of these things and do, for instance, top 100 df.explain, and it will show me the final query plan. And I can say explain true, and it will show me each stage of optimization, which is kind of fun. I'm not going to do that here because I'm kind of out of time. But again, not type safe, right? If I do a take on this, you can see that what I get back eventually is a row of things. And if I want to get back to something meaningful to the compiler, I've got to use as instance of, which I don't want to do, right? Because I could get that wrong. So here's the final bit that I want to go over, and that's data sets. So now I'm going to read this. There are 2 ways to read this in. Here's one. I can read the data set directly into a data frame and then do a .as string on it, and then do the parsing at the data set level. Or I can just take the existing DF, data frame, and do the as on that. So here I'm returning a triplet, right? And there's my data again. Now it's in a strongly typed string tuple, a string long tuple 3, right? And then I can do this as well. I think I'd much rather have it in a case class than a tuple 3 for access and readability. Do I still have my 7 point whatever million rows? I do. If I do a take on it, you can see that I get these edit objects back, and it came back fairly quickly. Right? And then here's my filter. Here's one operation. I'm sorry for the wrapping. If I get rid of the wrapping, you won't be able to read it. But you can see that I've put my filter in there. This is a standard filter lambda. Toss out anything that isn't the EN project and contains these weird characters that I'm not interested in. Do a group by on the page title. What the group by returns is this special thing called a grouped data set that has aggregations on it. This is exactly analogous to something called grouped data in the DataFrame API. And I imagine that those objects or those classes will have very similar APIs going forward. Map it so that I extract only the DS entry out of this, because that's all I want. And now because there's no order by, currently no sorting, I map it back to the data frame so I can do an order by, and then map it back to the data set. Not something I'd really like to do, but I can do it, and it does work. And then pull the 100 out, and this should give me the same results. And it does. And finally, and I'll do this really fast because I am officially out of time, I'm going to cache a couple of these and just show you what they look like in memory. So I'm going to take the data set that I was operating on. I'm going to cache that. And then I'm going to create an RDD that doesn't contain arrays of strings, but instead contains arrays of a case class, because that's going to result in a different kind of memory storage, right? So we're going to do that and cache that. And now I want to cache my data set that also has those edit objects in it. And as soon as these 3 things are done, we'll take a look at how they're stored in memory. I can look at the storage tab in that UI, and I can determine what is the memory efficiency of these guys. This is assuming they get done. So here we have 3 of them in memory. I think the 4th one is underway now. Yep, there's the last one. So let me refresh this. And you can see that the RDD, the unparsed RDD, the original one at the bottom, takes up about a gig. As soon as we add the case class, that's the top one, page counts parsed RDD. So now this is an RDD that doesn't contain just strings, it contains these case classes. Now the in-memory size has blown up to about just under 1.4 gig. But look at the data sets. The data set, the first one here, This is the direct string one, the second from the bottom. That's only 311 meg in memory. And even when we add the data set containing the edit objects, it's still only 323. Why? Because it's not actually caching the edit objects. It's using these fast encoders to translate them into this compact tungsten format, and that's what's being stored. So this is a fairly dramatic representation of how much memory you can save just by using data sets. And that's it. We're done. So I probably have time for one question. Okay, we got one question in the back, and then we're going to have to bolt. Yeah, so that's a good question. I really don't know the answer. The question was, so what's going to happen with the machine learning libraries? And what predicates that question is the fact that the original ML lib was based purely on RDDs. And then they said, oh, no, let's do ML and base that on this pipeline model with their data frames. And so the question is, will they be folding data sets into the machine learning library? Off the top of my head, I don't know the answer to that, but I can get the answer. Luckily, because I'm training with these guys, I can get back channel info to the development team. So I'll ask that, and I'll try to tweak the answer to that as soon as I find it. All right, okay, one more, that's it, and then I'm holding somebody else up. So how does it work with different data formats, like different file types? Right, so it's the same as with it works the same way as with DataFrames. So with DataFrames, what happens is that there are these adapters that allow you to read certain file types. The classic example that I like to give is built-in is support for text files, Parquet files, and JSON files, and as well as RDBMSs. So anything that has a self-describing schema like a Parquet file or an RDBMS is trivial to read into a data frame, because you can figure out the schema because the file actually has a schema. For something like JSON, they built an adapter and they included it in Spark, and by default it samples your JSON file. And it says, what are the fields in there? Because if you think about JSON, you can always determine the field names, right? And there are a limited number of types that can mostly be inferred from how the literals are expressed. And so what it will do is infer a schema out of that. And what if you have other ones that you need to be able to do? And the answer typically there is either look out on the net. There's this place called sparkpackages.org that has a bunch of adapters people wrote. So Databricks wrote one for CSV files, for instance, that will do that. Or you have to start with an RDD, read it in, parse the RDD into pieces, construct your own schema by a number of different means, case classes being the obvious one, and then move on.
My question was more about
Yeah, I think we need to take that offline. The question is how the as function works, and I think we could be here for 20 minutes talking about that, so why don't we take that one offline? All right, so I think if I read the schedule properly, we have another break at this point, and Brendan McAdams is up next. And thanks for your attention, I appreciate it.